speaker for tonight is Daniel Phillips. He is in the Department of Physics and Astronomy, and we shall welcome him, and he will tell you everything you ever wanted to know about physics. Go get him, Daniel.
Thanks, sir. All right. Well, while we're waiting a moment, I want to thank the organizers of the Science Cafe for this opportunity to speak, and I want to welcome you all here. I am not going to tell you everything that you wanted to know about physics, but I am going to talk to you about the symmetries of nature and how they inform our understanding of physics that takes place at very small and very large distance scales. However, it seems that there is an untimely problem with the projector, which was working just fine right up until when I wanted to speak. It's still up here. Yes. It's on. So, I mean, it was up right until I didn't even hit anything. Okay, very good. Okay, so before I go any further, let me just say that I'm a member of the Institute of Nuclear and Particle Physics here at Ohio University, and this is the area of physics in which I work. The Institute of Nuclear and Particle Physics includes those of us who are interested in physics at the subatomic scale, so the physics that takes place inside atoms. And one of the things we do is operate the on-campus accelerator, at the Edwards Accelerator Lab, which does experiments that help to uncover secrets of the nucleus. And the Edwards Accelerator is the largest accelerator in the state of Ohio. So there you go. Okay, so, okay. All right, so since we're in Athens, I thought I would borrow from the heritage of ancient learning with which Ohio University was imbued by its founders through being placed, hang on a minute, through being placed in a town with the impressive name of the ancient Greek capital. And so this is a picture of, I believe it's Plato and Socrates discoursing on the nature of reality. And Aristotle said that he was particularly fond, although he said it this way because he was Aristotle, right? He said that he was particularly fond of the mathematical sciences because they exhibited order and symmetry. And for the Greeks, this was a statement about the ideal forms of reality of which we only saw shadows in the world in which we lived. And so they understood that in some ideal realm, everything would be extremely symmetric. So over several hundred years, this led to the development of a cosmology. It really was a theory of the cosmos, which explained the motion of the celestial bodies. And for the Greeks, the motion of the celestial bodies was particularly interesting because it was not affected by the bad stuff, right, to use a technical term, right, the bad stuff that messed up the ideal forms that we had down here on Earth. So down here on Earth, the ideal forms were only seen as shadows, most famously in Plato's analogy of the shadows on the back wall of the cave. but in the heavens we could look up and see an expression of the true symmetries of nature. So for the Greeks, the most symmetric form was the sphere, and so they developed a cosmology in which all the heavenly bodies moved on spheres. And the Earth occupied the lowest place in this cosmology at the center of all the other spheres. And you can't see this because the print is too small, but then on successive spheres moving outwards from the Earth, the moon moved on one sphere, and then further out there were other spheres on which, for example, Mercury moved. The sun had its own sphere out here, and then furthest of all was the sphere on which the distant stars existed. Now, so this was a very symmetric view of the universe. In order to make it consistent with the observations that they saw, there were detailed calculations done of how the heavenly bodies moved on each sphere, involving, you may have heard of this idea of retrograde motion and epicycles, so more and more complicated motions as more and more detailed observations were made by astronomers. But you could make all this work. You could make this idea of heavenly bodies moving on spheres with the Earth at the middle agree with observation if you worked hard enough. So this was the dominant view of the universe for almost 2,000 years. And the first challenge to it was by Nicholas Copernicus, who pointed out that the Earth didn't need to be at the center of this cosmology, but the sun could be at the center. But Copernicus had a problem, which was that his explanation of the universe was not in as good agreement with observation as the existing one of Ptolemy and Ptolemy's intellectual forebears. So the real challenge came when Johannes Kepler took detailed observations of the planets and proposed his 3 laws of planetary motion, which hopefully all of you are, heard at one point. I'm not going to go through them in detail here. I'm going to show you a little movie. So my little movie... Oh, we went too far. So in the movie, the yellow object is the sun, because of course the sun is yellow, and the blue object is a planet. And so the planet moves in an ellipse around the sun. Now, for those of you who think that the Earth orbits the planet in a circle, you're almost right? So the Earth, it has an orbit around the sun that's almost circular, but it's a little bit squished, right? And that this ellipse, which is almost a circle, but it's not quite a circle, it's a little bit squished. If you go further out in the solar system, then the outer planets have orbits more like this, and these are not circular. So they're not, this perfect symmetric form that the Greeks thought that heavenly bodies moved on. But this, if you put this together with the idea that the sun is at the center of the solar system, then you can explain the observations very well. Now, Isaac Newton explained Kepler's laws of planetary motion through his application of calculus and his proposal that the force between a planet and the sun varied directly proportional to the product of the masses. Let me see if I can get this up here without obscuring it. And inversely proportional to the square of the distance between them. So this says that if planets are more massive, they experience more force, and this down here says that as you move, say, twice as far away from the sun, the force becomes 4 times smaller. Now, if I draw, the reason I've got this up here is that this is a picture of the force, right? So this shows how the force changes as you move outward in distance, and it also shows how the force changes as you look at different positions around the sun. And if I spin this for you, or if more accurately I get my computer to spin this for you, what you notice is that this force is circularly symmetric. It looks the same no matter which point you are at, as long as as long as you're at the same distance from the sun. So yes, it varies with distance from the sun, but it doesn't depend on where you are on a circle of fixed distance from the sun. So this force has circular symmetry, even though the orbits that it produces are not circles. And this is the first point I want to make, right? That symmetries of nature are not necessarily immediately apparent in the causes that are produced. So when physicists think about symmetries of nature, they think about the symmetries that the forces that produce what we see in nature have. They don't necessarily talk so much about what effects are produced. Or at least, to be more accurate, they make a distinction between the symmetry of the forces and the symmetry of the resulting phenomena. Okay, so I wanted to begin with gravity because it's the force that we all experience every moment of every day, and it's something that we're all familiar with on a very practical level. And also because it allows me to make this point that forces may produce effects that appear not to be symmetric when they themselves have a certain symmetry. For the rest of the talk, I'm going to talk about things that are more subatomic, because gravity, of course, operates on the largest distance scales in the universe, whereas the talk promised you that I would talk about the subatomic world. So I'm going to talk about two forces that are operative in nuclear physics, in the area in which I work. So there's the so-called weak nuclear force that governs the radioactive decay of certain nuclei. I'm going to talk about the strong nuclear force, which is the force that's responsible for holding nuclei together. So the thing that's novel about the weak nuclear force is that it breaks a symmetry between right and left. So you might think that I mean some sort of moral equivalence between these two people. This is not my point, right? My point is something more like this. So when a physicist says that there's a symmetry between right and left, what they're telling you is that if I start with a coordinate system something like this, so I label these axes x, y, and z, and being from the Commonwealth, I call it z. So if I label these axes x, y, and z, then I want to think about a way of defining right-handed that's independent of biology or chemistry or anything that's just I can think about for subatomic particles. So one way to do that is to think about how some particle is spinning as it moves in a particular direction. So if I had a particle, if you think about a top, right, and if the top was moving along the x-axis and it was spinning in that direction, we would say that that top was spinning in a left-handed way, because if I point my thumb along the x-axis and I use my fingers to indicate the direction of the spinning of the top, right, then that would be a left-handed spin. But what happens if I invert all the axes is the following. So I'm going to send all the axes to their opposites. So the x-axis now points the other direction, the y-axis now points the other direction, and the z-axis points the other direction. So this is what we find. This is called a parity transformation, and the point that this slide is intended to make is that under this transformation, my object that was originally spinning in a left-handed way is now spinning in a right-handed way. If I align my thumb with the new x-axis, then this thing, which I haven't changed, I didn't change the direction of the arrow, right, that thing is now spinning in the opposite direction. So what that means is that if there's some symmetry under parity, then forces shouldn't care about the handedness with which particles are spinning. Or to put it in more generic terms, there's a symmetry between left-handed parts of things and right-handed parts of things. Now, in fact, that symmetry is broken at an everyday level. So if you look at works of art, this by Picasso, for example, this work of art exploits a strong degree of breaking between the left half of this lady's face and the right half of her face. And you don't have to look at just modern art to see this kind of breaking between left and right. If you look at the Mona Lisa, for example, then and you assume that the Mona Lisa was parity symmetric, you get kind of an ugly result. Not good, right? So although Da Vinci was a great scientist, he clearly understood that parity was not a symmetry that we like to look at in terms of people's faces, and so he came up with a much nicer result. So all this kind of symmetry breaking, though, is like the symmetry breaking of the planetary orbits. It's a symmetry breaking in the effects and not necessarily a symmetry breaking in the forces. Right. So the most enjoyable example of this that I know of is the fact that there is a particular species of snail whose shell occurs in two different windings. So if you look closely at these pictures, you'll see that one of these two snails has a shell that's wound in a let's see which way it's this one. So this one is in a left-handed way, right? And the other one has a shell that's wound in a right-handed way. So a priori, you, or before, without knowing anything else, you would think that both of these were equally likely outcomes, because who's to say whether the snail should have a left-handed type shell or a right-handed type shell? But it turns out that there's a reason why certain types of shell are favored over others, and that's because it's easier for this snail's snake predator to eat the snails with shells that are wound in a particular way, as you will see in this video. So if the shell is on in the other direction, it can't do that, and the snail survives. So evolutionarily, the snails with a particular shell orientation are favored. But again, right, that's not the kind of, although that's fun, that's not the kind of symmetry breaking I'm talking about, because the forces that produce the snail, which are going to be, it's going to be essentially, that's going to be forces that underpin chemistry and biology. That's predominantly the forces of electricity and magnetism. Those forces look the same whether I look at them from the left or the right. So the question as a subatomic physicist is there any force that doesn't obey the symmetry between left and right? And the answer to this for a long time was thought to be no, until Madame Wu did a famous experiment in the mid-1950s where she considered the decay of a radioactive nucleus called cobalt-60, and she showed that the electrons that are emitted in this decay, so here I have a little cartoon of the decay, so the nucleus decays to this other nucleus called nickel-60, and in the process it emits an electron and another subatomic particle called an anti-neutrino. And so in doing this, she showed that only left-handed spinning electrons are emitted. So that meant that this decay violated parity symmetry maximally. If parity was a symmetry of whatever force governs this decay, then you should see an equal number of left and right-handed spinning electrons, and in fact only left-handed spinning electrons were seen. So the physicists speak for this is that the weak nuclear force has maximal violation of parity. It completely breaks this symmetry between left and right, which is a symmetry of gravity and a symmetry of electricity and a symmetry of magnetism. So this is the first example that anyone had observed experimentally of symmetry breaking in the force itself. As I said, there are lots of examples of symmetry breaking between left and right in nature, but all of these result from forces that themselves look the same whether you look at them from the left or the right. And this is kind of interesting if you care about such things, because what it means is that this is a way to define left-handed that's independent of biology and chemistry. So if you've ever thought about trying to communicate to an alien civilization who might have completely different biology to us what left-handed and right-handed is, then this would be the sort of thing you would have to tell them about, because otherwise you don't know that you're talking about the same thing as they are when you talk about left-handed and right-handed. But one of the issues with actually seeing this experimentally, and the reason it wasn't discovered experimentally until the mid-50s, is that the weak nuclear force is called the weak nuclear force for a reason. It's weak, right? So if I look at two protons separated by a distance that's typical of the inside of a nucleus, then the weak nuclear force is about 1 part in 10 million the strength of the force that actually keeps the nucleus together. So when you're going to do an experiment to find parity violation, you need to count very, very carefully. So for example, experiments done in the 80s in various laboratories took a beam of protons and bombarded a target with hydrogen atoms, and what they were looking for was parity violation in the collision between the proton in the beam and the protons inside the hydrogen atom inside the target. So some of the time the proton would go to the left, some of the time the proton would go to the right, but if there's parity violation, the difference between left and right is small but non-zero. So for instance, this experiment done in Bonn in Germany found that about 1 in 10 million protons went, I think that was left rather than, it's negative, so that one is right rather than left. Okay, so this is something that I've worked on in the last few years, and so we think that we understand how this comes about based on the fact that there are small but non-zero effects of the weak nuclear force inside the protons that participate in this experiment. So even though the weak nuclear force is small, it is detectable, and it's from that point of view understandable why the experiment that looked for this effect saw what it did. So I want to finish my part of this afternoon's effort by talking about the standard model of particle physics, which I'm sure many of you have heard about, in particular in light of the recent discovery of the Higgs boson. So the standard model of particle physics is formulated in terms of quarks and so-called leptons, and then particles that generate forces between these other particles. So I'm not going to, this is not a standard model talk, so I'm not going to go through how the standard model is constructed and all those things, but I want to pick up this idea of symmetry, and talk to you about a different kind of symmetry which governs the physics in the standard model. So to do that, I'm going to focus on the quarks up here in the corner. So these are the subatomic particles that live inside protons and neutrons. And just so you know, for most of your, so all the matter that you will encounter in your life is made up of stuff in this column. So up and down particles and electrons and neutrinos and antineutrinos. So unless you are a nuclear or particle physicist, in which case you may make stuff out of these other particles. All right. So for the moment, let's just think about stuff in this column, and in fact, let's just think about stuff that's inside protons and neutrons, so up and down quarks. So in fact, I'm going to make this even simpler. Let's think about a particle that's constructed out of 3 up quarks. So here I've drawn something constructed out of 3 up quarks. It's kind of like a heavy proton. If I turned one of these into a d quark, this would be a proton. So I've drawn these in 3 different colors because what physicists came to understand in the late 60s and early 70s is that not only did quarks come in those different UDSCTB things, which we now call flavors, but they also came in different colors. So this is kind of like ice cream, except it's ice cream where you could have strawberry ice cream that was colored blue, right? So if you've ever gone and gotten blue raspberry frozen yogurt, you know exactly what I'm talking about, right? So in this case, your quark not only has a flavor, it has a color. So I'm working with quarks that all have the same flavor, so they're equivalent, but they have different colors. And it's a fact which I'll attempt to explain in a couple of slides, but for the moment you just have to believe me that inside a particle like this, there'll be one of each of these 3 kind of colors. So let's call them 1 red, 1 green, and 1 blue quark. Now, the reason we want to understand this is because all the properties of this particle are determined by the forces between the quarks. That's what subatomic physicists do, right? They try to understand why this particle does what it does, why its mass is what it is, why its size is what it is, why its radioactive decays sort of things are the way they are, based on the forces between the quarks. So this is just like if you want to understand the properties of an atom, you try to understand how the electrical and magnetic forces between the nucleus and the electrons that are orbiting it and the electrons themselves determine the properties of the atom. So subatomic physicists who are trying to understand the properties of this particle also want to know about the forces here. But the force that's operative here is not electricity and magnetism, it's the strong nuclear force. It's the force between these quarks. So key to understanding that force is the fact that there are three types of quark, and the force between these quarks should be unchanged by a relabeling of the colors. So you assumed that I was calling this one red and this one green, but it doesn't have to be that way, right? So someone else in the room might want to call this one green and this one red, right? Or they might even want to substitute red for some funny combination of red, blue, and green. So in this kind of symmetry, which is a different kind of symmetry to anything that I've talked about so far, you say that the theory has to be the same if you relabel these particles in some way where you just switch all the labels around, right? And if the theory is not the same, it's not a viable theory. So the mathematical language for this is that the theory should be unchanged by transformations in the symmetry group SU3, right? So the 3 indicates that there are 3 objects that you're changing, and this stuff has to do with what sort of combinations you can form. If anyone wants to ask me, I'll be happy to say more about that. But the point really is that you should be able to relabel these quarks, since they're all U quarks, they're all the same, you should be able to relabel them red to green, green to red, blue to red, or some combination thereof without changing the forces. But in fact, and this is the really remarkable thing, more than that is true. So the theory that underlies quark dynamics has the property that you can relabel them in different ways at every point in space and at every point in time. So it was like saying that everybody in this room could choose a different labeling, and the theory should still be the same, right? So if we all agreed on a labeling, on a way to change things, that would be one thing. That's called a global symmetry, right? But if everybody in the room chooses a different labeling, that means that the labeling at every point in space and time is different. And the forces have to be the same under this relabeling. So this is called a local SU3 color symmetry. And it turns out that this puts remarkably strong constraints on the theory you can write down. So the theory that was written down as a result of postulating that this was the symmetry is this. I'm not expecting you to memorize this, although it will be on the final. But it's sort of a remarkable formula because you can write it on a t-shirt and it leads to a remarkable variety of phenomena in terms of the properties of subatomic particles. One of the most interesting phenomena it leads to is so-called asymptotic freedom. In layman's terms, this just means that if you look at the force between two quarks, the force between two quarks gets weaker and weaker as you bring them closer together. So that's actually this part of the curve out here. This represents the strength of the force, and as you go further and further this way, the strength of the force goes to 0. So that's kind of unusual, right? In any other force that you're used to, whether it's gravity or electricity, if you bring two things closer together, they attract or repel each other more and more strongly. If you think about bringing two magnets together, at some point they glom onto each other. This is like the opposite. If you bring two quarks together, as they get closer and closer to each other, they'll interact less and less strongly until, in the limit that they're right on top of each other, they don't interact at all. And that's why it's called asymptotic freedom, because as they get infinitely close to each other, there's no interaction at all. Conversely, if you take them further and further apart, the interaction gets stronger and stronger. And it's this fact, so-called confinement, that necessitates that the objects that you build out of quarks have some combination of red, green, and blue that produces no overall color. Because quarks are an interesting philosophical object, because quarks have never been detected in an experiment. Because you can't liberate them from the bonds of their color forces, because as soon as as the further apart you pull, so if I try and pull one of these quarks out of my subatomic particle, as I pull it further and further apart, the force will get stronger and stronger. Nevertheless, by a variety of experiments, we now understand the way this force drops off as the quarks get closer and closer together, and we understand through a combination of experiments and detailed computational modeling, how those forces produce the properties we see. We do, if you like, the chemistry of subatomic particles. And because of that, we now have a better and better understanding of the nucleus. So this is my helium-4 nucleus. This is a helium-4 atom. It has 2 electrons. And in here, I have 2 neutrons, these guys here, and 2 protons. And what this picture doesn't show is that inside these neutrons and protons, these would have to be all different colors. But it shouldn't show that, right? Because the way that you label the colors is up to you. It should be independent of the particular labeling of the colors that you choose. Okay, so let me finish up so you guys can ask questions. So I've argued that understanding the symmetries that are operative in nature helps us to work out the 4 different forces that cause particles to interact. So those 4 forces are, as I'm sure you all know, gravity, electricity and magnetism, that's one because it's the same thing, the weak nuclear force, and the strong nuclear force. I didn't talk about electromagnetism here. If anyone has questions about that, I would love to answer it just so I could complete my set of 4 forces. Right? Okay. Now it turns out I talked about 3 different kinds of symmetry in this talk. I talked about so-called continuous space-time symmetries. So this is like the idea that gravity looks the same no matter where you look at it from, as long as you're at fixed radius. This is a so-called rotational symmetry. But forces are also symmetric under translations. And Einstein famously postulated that forces should also be symmetric under the motion of observers as long as they were moving without acceleration. And this is the underpinning of his theory of special relativity. So imposing those symmetries on putative theories of nature helps to constrain what those theories can do. And one of the points of this is that those symmetries can be present even when it's not obvious that they're present. So if you think about the ellipse, it doesn't look rotationally symmetric. If you look at an ellipse, it matters whether you're at the flat end, whether you're at the long end or the short middle, what you see, but the force that produces that ellipse is rotationally symmetric. Conversely, things like parity or famously the idea that physics should be invariant under reversal in time, those seem kind of obvious things for forces to obey, but it turns out that those symmetries of nature are broken, and in particular both of them are broken by the weak nuclear force. So these discrete space-time symmetries are different from continuous space-time symmetries because it's essentially a switch that you flip. It's not some continuous thing that you can do. And lastly, I talked about so-called internal symmetries. These are these relabeling of particular particle properties, right? So the standard model of particle physics is in fact a statement that nature is invariant under certain internal symmetries. There's the color symmetry that I talked to you about, and there are also other symmetries associated with the other sectors of the standard model. And moreover, that those internal symmetries are local in the sense that you can make different relabelings at different points in space and time. Now, to bring this back to ancient Greece, right, I want to point out that this is actually a very democratic idea. Right? So the point here is that the description of nature shouldn't be affected by what angle you look at the system from, or which you choose to call left and which you choose to call right, or which way you label your quarks. So in all of those choices should leave your description of nature unchanged and should lead to the same consequences. And so it's with that democratic idea that I will conclude my talk. Please.
How does the force grow when they're being pulled apart, or how does the force decrease when they're put together?
So, okay. So when you say how, okay, so, I'm sorry, what's your name?
How or why?
What's your name?
Nostrato?
Nostrato? Okay, so Nostrato wants to know how the force decreases when the particles are pushed together or how it increases when they're pulled apart, right? And so I was going to ask you, did you mean how in the sense of like quantitatively, how does it change, or how the heck does that work, right? So let me answer the first one first because that's easier. So the how is that if you go to short enough distances, the force between two quarks would be some number divided by the square of the distance, sort of like gravity, right? But that number upstairs keeps getting smaller and smaller as they get closer. So this is how that happens. So it's like gravity, but with a varying gravitational constant, and the gravitational constant gets smaller as they get closer together, right? As you go to long distances, things get more complicated because you need to consider lots of stuff happening between the quarks because the force isn't weak anymore. So if the force is not weak, that means there are many, many things that can happen, right? And so in that case, as far as we can tell, the force under some approximations the force goes to a constant, right? The potential grows linearly, okay, but the force goes to a constant, right? So it's a constant attractive force, but you can never get away from this, right? So in that sense, the quarks are never free because they always feel this constant force sucking them back in. Now, in terms of how that's possible, so one way that that's possible is that we think that as the quarks get pulled apart, the force develops through it essentially becomes some tube-like entity that carries the force rather than being something that's spherically symmetric. But again, right, even though you have a effect that is not spherically symmetric, the underlying theory still has rotational symmetry. Okay? I don't know who was first over here, so you guys will have to sort it out.
So back to like the asymptotic freedom. What's stopping the, like, if you have in a nucleus you have two protons together, what's stopping the quarks in between those two protons, like, interacting with each other?
Oh, so this is a really interesting question, right? So because it's true, right? So actually, let's look at this picture. So there are residual interactions between the quarks in different protons and neutrons, right? And those actually, so one way to think about what the force is that binds the nucleus is as a result of those residual interactions. So just like if I was a chemist, I might say, oh, so I built an atom over here, and this atom is electrically neutral, right? It has a proton with, it has a nucleus with 8 protons, but there are 8 electrons orbiting, so I guess this is oxygen, right? So I have an oxygen atom over here, and I have another oxygen atom over here. It's electrically neutral, but if they get close enough, then electrical forces allow them to share the electrons, and then I get an O2 molecule, right? So in the same way as the residual interactions, even though you build an electrically neutral object, produce molecules, in this case, the residual interactions between quarks produce nuclei. All right. Now, to calculate that computationally is actually very intensive because you have to first solve the problem of what the quarks are doing inside the protons and neutrons, and then you have to bring a bunch of protons and neutrons together. But it can be done, and this seems to work in the sense that it produces nuclei with the right masses and properties if you figure out what should happen from that fundamental picture in terms of quarks. Yes?
I was wondering if you could expand on what color means, what it affects, because it sounded like you were saying that the like up, down, top, bottom, what affects is the strong force. So what we can just freely sort of pick the colors?
Okay, so it's just a label, right? Okay, so as I'm sure your parents and teachers tell you, you should not take labels too seriously, right? But it is true that there are 3 different kinds of up quark. So even once I fix the flavor, there are 3 different kinds. Okay, so now we're going to pick some labels, right? But the point that I was trying to make here is that if someone else picks different labels, that shouldn't change the physics because it's just a label. Right? And that's the essence of an internal symmetry, is that someone else could pick different labels and they should get the same answers. Okay. Now, I think you were also asking me, so why isn't that true for flavor? Right? Why isn't it true that I can also reshuffle the labeling of up and down? So to some extent it is, right? And at the nuclear level this leads to an approximate symmetry between neutrons and protons. But it turns out that up and down quarks are different, right? So the up quark has a different electrical charge to the down quark, and it has a slightly different mass, right? So anything that's affected by that is going to be affected by a relabeling. And so that symmetry that results from a reshuffling of flavor is only approximate. Right? As far as we can tell, different colors of quarks all have exactly the same properties, and so you can relabel them any way you want. Okay.
On that slide you were just on, there's a category called leptons. What are those?
So I think, so my Greek is not very good, right? Despite my effort, to tie myself to the tradition of the ancient Greeks. And so I think it has to do, I think lepton has to do with the fact that they're light particles. So generically, these particles are lighter. If I look in any column here, these guys are lighter than these guys. Okay. So what's the difference here? So the difference here is actually that these ones interact primarily but not exclusively through the strong nuclear force, through this quantum chromodynamics, this theory of color that I described. And these ones don't experience the strong force. These ones experience only electromagnetic interactions and interactions through the so-called weak force, or what I call the weak nuclear force. Right? So it's a little bit ironic here that the weak nuclear force started off as something in nuclear physics, but it actually operates also between leptons, but it's true, right? So, and in fact, the fact that there are two symmetry groups here is exactly related to the fact that these guys experience those two different forces of nature. Okay, hi.
So you spoke about how quarks make up neutrons and protons. Do we know, or are we looking into like what makes up quarks? And could you also touch on like what is the Higgs boson?
Okay, so the question is, do we know what makes up quarks, and can I touch on the Higgs boson? Okay, so yeah, I think the people at CERN would be very upset if I tried to touch their Higgs bosons, right? So if I so let me answer the first question first, right? So there have been a number of searches done for quark substructure, right? And in a sense, it's very logical, right? So I told you, that atoms have neutrons and protons inside them, and neutrons and protons have quarks inside them. This is like the joke about, I don't remember which famous physicist it was, but an old lady comes up to the famous physicist at the end of his talk and says, I understand how the universe is supported. And they go, oh yes, really? How? There's a turtle, right? The whole universe sits on the back of a giant turtle, right? Oh yes, okay, very good. And what's the turtle standing on? Oh, another turtle. Okay, and what's that turtle standing on? Oh, another turtle. And oh really? And what? She goes, no, you can't get me that way. It's turtles all the way down. Okay. So it's very tempting to think that it's turtles all the way down, right? That there are new and new layers of substructure all the way down. So because of that, people have gone looking, and all I can say is that at the highest energies that we've looked, which means at the shortest distances that we can probe, the quarks appear to be point-like objects. They have no substructure. So there's a number on here. Where is it? So here, the size of the quark is less than 10 to the minus 19 meters. So if you compare that, so we've got to talk about distance scales here a little bit. So the width of a human hair is 1/millionth of a meter, right? An atom is approximately, biggish atoms are like 1/billionth of a meter. Okay, so then what are we going to do? So then the size of a nucleus is 1,000,000 times smaller than that. Okay. And then this here is then 10,000 times smaller again, right? So you can't rule out the possibility that there's substructure, right? But as an experimental statement, insofar as we've seen they're fundamental, right? They're what the Greeks actually thought that atoms were. They are building blocks of nature with no internal substructure, right? And for all practical purposes, if you can't see their substructure experimentally, you might as well go building a theory in which they're fundamental. At least that's my approach. I think, yeah. Wait, I still haven't touched the Higgs boson. Okay. So the Higgs boson. When was that? 2012, right? July the 4th, 2012. CERN announced that the two independent collaborations had observed a particle with the properties of the Higgs boson or something. They were very careful at first, but they would now, after taking more data, they're now convinced that what they saw is the Higgs boson. It's an important piece of the Standard Model because it helps you to understand why the weak nuclear force is weak. So without the Higgs boson, you don't understand why the weak nuclear force is, for instance, so much weaker than electromagnetism, because that weakness actually has to do with the fact that it's a short-ranged force, and that short-ranged force has to do with the fact that these guys are massive, and the fact that these guys are massive comes from the Higgs boson, right? So that's why the Higgs boson is important, because it tells you, I would say, because it tells you why the weak nuclear force is weak. Okay, yeah. Please.
A little bit more philosophical question. Given that the different colors of our up and down colors are essentially identical in properties, and that facilitates some freedom of labeling, what are grounds for distinguishing their two types?
Okay. Right. So the question is: so if I say that there are three different colors, but I also said that they all have the same properties, then isn't it redundant to have three of them, right? So the answer to this question is probably that I misspoke slightly when I said that they all have the same properties, because they differ in how they experience the strong force, right? So in particular, so I didn't go into this because it was a 30-minute talk, right? But quarks can change color, okay, and they change color by emitting other particles. And so you can start with your red quark, for instance, and it emits something that is some combination of red and anti-blue, and it becomes blue. So color is conserved in this interaction, but then that red anti-blue object has to go somewhere and hit something. Okay, and so that's like the hand-waving description of what the stuff I wrote down on the next slide is, right? But what that means is that you need the three colors in order to generate the color forces in this theory, because it's the exchange of these color, anti-color objects that generates the forces that bind this thing and keep it together, and then ultimately determine its mass and its size and its decays and all those other things that we try and calculate. Okay, does that answer your question? Okay.
Our last formal question is going to be the young man.
Okay.
So could you talk about the difference between like the weak and strong nuclear forces, like what causes them to be different?
Sure. So for that, I'm going to use, this picture. Not that picture. See, this is the problem with putting animations in talk. Okay, so in the Standard Model, forces are generated by the exchange of particles. Okay, so these things that I was describing, the color, anti-color, the colored stuff that quarks spit out and suck up to generate color forces, those are called gluons, right? Because they cause protons and neutrons to stick together, right? We're really not very imaginative with our naming, but it's okay, right? So that's this guy here, the little g, and gluons, as far as we can tell, have no mass, right? So that means that the force, at least at short distances, is it doesn't cost so much to emit them, and so the force is stronger than the weak nuclear force. As I just commented, these guys that transmit the weak nuclear force, they have mass, right? And the Higgs boson is essential to generating their mass, right? So it's the essential difference in the mass of the stuff that's being exchanged that causes the weak nuclear force to be so much weaker than the strong nuclear force, right? That, at least at the distance scales at which I do physics, right? There is also another effect that the strength with which the stuff couples to quarks, for example, is also different. But the predominant effect at the scales at which I do physics is associated with the type of stuff that is generating the forces between them.
It's a good question. There were people in front of you, though. Are you going to, All right. So that was our last point. It's about 6 o'clock, just so if people have classes or other places they need to be, I'm sure Dr. Phillips would be happy to stay here and answer questions and talk to all of you guys more about this. The one final announcement that I have is in 2 weeks, we have the next Science Cafe, which is Sarah Hamandi from Mechanical Engineering, and she's going to talk about the physics and future of cornstarch. What did cornstarch do for you lately? Okay, guys? All right, please thank Dr. Phillips, and I'm sure he'll entertain questions.